Okay, we're going to try this. I got 25 minutes to try to get this done. We're going to look independent variable, a variable that is thought to or may cause or influence another variable, dependent variable that may change based on the independent variable. Now, I'm using some stats examples. I go a little bit more numerical at times, but I want you to look at these. I got two variables. You can determine which one you think typically is the independent variable, which one's the dependent variable, which one might cause the other one to make a change when you change it. So pause the video. I'm going to give it about 5 seconds, and then I'm going to move on. If you don't pause the video in that time, if you want to discuss this, whatever you want to do. Okay, going on here. Now, I didn't make it real tricky. So I would say the amount of water is probably the independent variable we would typically look at, and the plant growth. Now, at any time, you can investigate and you can switch these around, but how much water you give, that's going to affect the plant growth. We would believe that to be true. Time spent studying, AP Psych grade. Okay. We can, of course, like I said, reverse it, but the time spent studying typically is going to help us determine or influence our AP Psych grade. Student height and GPA. Now, typically when somebody, I always say when somebody walks into class, if there's a physical characteristic, we would probably put that one as the typical independent variable. You can switch these around. You could study, does your GPA affect your height? That would be a strange question, but we'll talk about that one. Does student height influence the GPA? Probably not. We'll talk about that one. Weight of an elementary student and their reading level, we'll discuss that one, but we would put the weight of the elementary student and what reading level they read at. Does that have an influence on anything? Okay, so first we're going to talk positive correlation. In your review, it says positive correlation. The presence of one predicts the presence of the other in stats. As one increases, the other one increases. Okay, so if somebody spends 0 hours studying, we might expect that they probably won't have a very good score. Now, a 1 is the lowest you can get on any of the AP tests. So hopefully that's not what's going to happen. You spend 80 hours studying, maybe you'll get a 5. Now, we would think that it's not going to be this perfect correlation. If all things are in a straight line and they're going up positively, that is a correlation. Correlation is numerical value. That's a perfect correlation. R is 1. It could have a very strong correlation. It might have a weaker correlation, but it's likely a positive number, and correlation is that number R that we get when we're investigating this relationship. So I'm going to put this one up there. Would the weight of an elementary student and their reading level, would that have a positive relationship? You can again pause the video if you want to discuss that quickly as a class, or just think about that. Would that be true or not? Okay, now of course this actually is true. Right now you're in shock. You're saying, what? The weight of an elementary student would affect their reading level, and it is actually true. If you were to graph this, you would find a positive relationship. So I know there's shock and awe going on in the class, but this is one I always use because it introduces a concept of a confounding variable. And I don't know what happened to my numbers over here, but they got kind of weird in the print. But a confounding variable, the word confounding means confusing. There's a confused result in here. And that's because the age of the student is actually causing both variables to rise. Because if you have a first grade student might weigh like 45 pounds, for example, and is reading at a first grade level. But a fifth grade student might be 85 pounds and they're reading at a higher level. They're reading at a 5th grade level. And it's not going to be a perfect correlation. Here I would have an R of 1. We, of course, know some 1st graders might read at a little higher level. Some 5th graders might read higher or lower. But overall, we're going to see as their weight increases because they're getting older, their reading level is going up. All right. So that is an example of a positive correlation, but it's a great example of a confounding variable, something that is confusing the results that we would want to separate out. Okay. So good grades and number of skips. If we had to talk about this, we might have what we call a hypothesis. Now, the way your book or your review book, at least, it says a hypothesis expresses a relationship between variables. A change in an independent variable will produce a change in the dependent variable. So here's our hypothesis. And this one is going to result in a negative correlation. We're saying more skips result in less good grades. Now, you have to define things. And if I'm defining things here, I might call, let's say, a good grade. We have 6 classes at Washington High that you're taking, and you define a good grade as an A or B, and anything under an A or B, C, D, or failing grade, that you would call that fewer good grades. So somebody who has no skips has all A's and B's. So they have, 6 of those. But somebody who has 47 skips, they only have 1 A in a class. I don't know how they got their 1, but we would probably see a negative association. Now, a negative association, I didn't put that definition on here, sorry about that, but as one increases, the other one decreases is the way we define that in stats. So you would say in psych, the presence of one, there's a lack in the other one. So more of these skips, we have fewer of the other one. Okay, now typically here, we're just talking like slope in algebra. If I was teaching algebra, as we walk on this line from left to right, you're going down. If you're walking on a line from left to right, if you're rising, that's a positive slope. I would recommend that if you can think about things and try to graph them. I'm a little more visual, so a lot of times, I show things the way that I think. If you can explain it to another student in the way that you think about those, and you understand that, that's the goal. Okay, here's a hypothesis. People who eat salad every day have less cavities. Okay, so now if we're talking about this, maybe we put down here the amount of salad. Now, again, you can't always graph everything, but I'm thinking of the idea, you eat 0 salad, you have a lot of cavities. So over here is number of cavities. Okay, you eat more salad, you have fewer cavities. Now, does that mean it's necessarily a cause-effect situation? And this brings up the idea of what in statistics we call an observational study. I believe you call it naturalistic observation. The people are making a choice. They're choosing to eat the salad or not eat the salad. And when people are choosing, you do end up with confounding variables, because what other things might they choose? They might choose to brush their teeth more often. And then the brushing of the teeth is causing the increase, because maybe brushing your teeth because you care about your body, you're trying to eat more salad, what's good for you. Maybe it's also exercise, and that goes in there, but there's a lot of confounding variables. When people get to choose what group they're in, you introduce confounding variables. One of the goals of what we call experiments, of course, is where we assign them what to do, and that should eliminate a lot of the confounding variables. If we were to graph student height and GPA, I don't think there'd be much of a relationship. For instance, freshmen might be shorter, and some might have a poor GPA if we're looking at their GPA 2.0, 4.0, but we've got some freshmen who have a 4.0 GPA. We have some seniors who probably have a 2.0 and some seniors who have a 4.0. Things like that. And overall, we're not going to see a positive or a negative relationship. The worst correlation you can have is one where R is 0. If you have your correlation and they're perfectly in a straight line, but they're going negative, that's a correlation of -1. That's a perfect correlation. It has a perfect relationship. And that's the best correlation you can have in terms of a negative correlation. If they're all in line and positive, that's a correlation of 1. Now, typically in statistics and probably psychology, you're not going to get perfect correlations. The only way we get perfect correlations in statistics, if we do something like this, all right, we go 12 inches is 1 foot. Conversions, okay, 24 inches is 2 feet. And no matter what we do, we go 36 is 3. They're going to be in a straight line. All conversions end up with perfect correlation. But statistics, when we're sampling stuff, they usually don't end up that way. All right, plant growth. If we give a plant 0 water, it's probably going to have no growth. It's just going to die. Okay, but we give it a little bit of water, it grows a little bit more, a little bit it grows, and it's probably not some perfect relationship, but the more water we get, we would probably expect a positive relationship. But there is the idea of all of a sudden we give it a lot of water and we see the plant's not doing as well. What happens is the roots of the plant, if it has too much water, it doesn't get any oxygen, so the roots don't get any oxygen, so therefore the plant really, in essence, starts to drown, and you can end up seeing a negative relationship. But that one that falls outside the pattern, we call that an outlier. It's an extreme score. A lot of times we want to investigate, maybe it starts to change and go negative if you give it too much water, and there's an optimal amount of water that we can give a plant so it can grow. All right, now in statistics, we talk about 2 types of random, and I believe you have the same 2 types that you always talk about. We have random sampling, and that's the idea where we might put everybody's names in a hat. And we'll a lot of times say, let's put them on some uniform object like ping pong balls or something like that. Write your name on a ping pong ball, and then we make sure we shake the hat to make it random, and then we might pick. So in here, if you have 30 students in your class, we shake the hat and we pick out 5. That's our random sample. That's different than random assignment. Random assignment is where maybe you have 100 volunteers and you're going to assign 50 are going to get a placebo. So they're going to have a treatment that's not known to work, and 50 are going to get a drug, okay? And they're randomly assigned to those 2 groups. Those are 2 different types of random, and you have to recognize those types of random when you're doing things. Okay, so experiments, observational studies, or naturalistic observation. What's the difference in an experiment? People are randomly assigned. So that's that idea that I was showing here. We randomly assign them. They're not just randomly picked. Observational, people might choose which group they're in. A good example, typically, if we're studying smoking, people choose to smoke. So we might see some health situations in that, or but they choose to smoke or not. We're probably not going to do an experiment. All right, so one of the questions you had on here, it says psychologists prefer the experimental method to observation because, and the main reason you use experiments is experiments can show cause effect. If people choose, you end up with all sorts of confounding variables in there. So you want to know that that's the reason we want to assign people to those groups. Second question, number 4, which of the following hypothesis would be most difficult to test experimentally? So you look, as you look through here, we could assign people to be exposed to red or not be exposed to red. We could assign people to exercise or not. We could assign people to watch violent television or not. We could assign them to study or not. And, we could have them not study for a test or study for a test. But this one, divorce makes children more independent. Okay, we're not going to assign people to get divorced or not get divorced. That's something that happens. So you observe that, and that would be a great example of experiment and observational study. Okay, now skew. You have to remember the stretchy part is the skew. We call it skew to the right. You call it positive skew. And the reason you're calling it positive skew is because on the number line, the positive numbers are to the right. So where is the stretchy part? remember this, if it stretches to the right, the mean is going to be bigger than the median. The skew, I don't know, the skew always pulls the mean, okay? So the mean always ends up being higher. If you know it's skewed to the right, the mean will be higher than the median on the number line. If it's skewed to the left, which you call negative skew, on a number line, this one, the stretching part goes to the left, so the mean is going to be lower than the median. Those are some key concepts. I know there's always questions on the psychology test, also the AP stats test. So if we're looking here and we're saying, what might the mean and the median be? I think the median would be maybe about 1.9. It's going to be pretty much in the peak. But the mean would be lower because the mean is going to get pulled down to the left because of that. So the mean is less than the median on that graph. If we see a skewed right curve, the median maybe is about 25. So I think the mean is going to be bigger than 25. The mean is going to be greater than the median because the mean gets pulled in the direction of the skew. All right, now this one, back in Algebra 2, you memorized some values. In statistics, we try to remember that if you go from one standard deviation below to one standard deviation above, there's 68% of the curve. If you go from two below to two above, there's 95% of the curve. So we call this rule the 68, gotta write the right number, 95, 99.7. If you go from 3 standard deviations below to 3 above, you have 99.7. Your other option is to go back and to memorize all those little pieces in there that you memorized back in Algebra 2. That's something you memorized in Algebra 2. If you are you allowed a calculator on the psych test? No. Okay. So, all right. So one of the things is I would draw. Okay. Anytime you have a curve, learn to draw the curve. The way we draw the curve is we make this thing and it's an asymptote. It gets closer on both sides, and you draw 1, 2, 3 lines this way. A curve typically will only go 3 standard deviations up and 1, 2, 3 standard deviations down. And if you learn to draw, I think most questions end up pretty easy. This is the mean, and you always add a standard deviation, So when you get a question like this one, okay, it has a mean of 100. The mean is in the middle. And that's what we call a 0 z-score. If you draw the 3 standard deviations up, 1, 2, 3, and the standard deviation is 15, you add it on. So you add on 15 again, add on 15, and then if you compare it, it says, what is her z-score? Her z-score is 3. All right, bell's ringing. Somebody want to go in the hall and tell everybody to be real quiet as they come in. I'm going to try to finish in the 7 minutes here. Okay. So, mean, median, mode. Mean is your average. So hopefully, since you don't get a calculator, the mean is the average, and that is also that middle of the curve. The median is the middle number, but they have to be in order. The mode is your most common number. Okay, so you get a question like this one, maybe. Oh, I don't have it in there. Okay, I'm just going to do this problem number 2. Theoretically, random assignment, I should have had this one in a different place. Random assignment should eliminate most of the confounding variables. What happens when you separate them into the groups randomly, I have 50 in this group, 50 in this group, you should get all of the different variations in the groups taken care of. Oops, I don't know what happened here. All right, this is the one I was looking for. What is the median of the following? Remember, when you're doing the median, you have to put them in order. So you have to say my lowest number, next lowest, next, keep going, 6, 7, 9. Okay, with an even amount, you're looking for the middle. So the middle is in between those two numbers. So we have to average those two. 4 plus 6 is 10, divide by 2. Our median needs to be 5. If I have a simpler version, 1, 2, 3, 4, 5, what's the middle? The middle is directly in the middle there. That would be a median of 3. So if you can just tell everybody to hang out in the hall, and I'm going to try to get it done in 4 minutes. We'll see, or I'm going to just stop where I'm at. All right, the treatment group receives the independent variable. So they receive the treatment. You shouldn't use treatment group, or we call it the experimental group, but that's the one that receives the treatment. If it's treatment group, you should never use a word to treatment group receives the treatment. Use a word to define itself. That's poor academics. Control group receives nothing or a placebo. Now, there's goals in that. I'll just use this real quick. But if I assigned everybody to exercise, I wouldn't know if exercise is improving sleep or not, for example. So I have some people to exercise and some to not exercise, because I could end up with a confounding variable. If everybody exercises, then all of a sudden they start eating, and because they eat more, they sleep better. Who knows? Okay, if somebody is exercising, some not exercising, we're trying to measure the amount of sleep, then we might get that idea better. Single blind. One group doesn't know. Now, in statistics, we don't care if it's the subjects or the others, but if in your book it says the subjects don't know what treatment they received. A double-blind experiment is where both the evaluator and the subjects don't know. Okay, so really hard to have any type of blinding. If we were going to test some people in a green room and some people in a blue room to see which room you test better in, green or blue, that would be hard not to be aware that you're testing in a green or a blue room. But if we're trying to figure out, some sort of sorry, my brain went blank, so I'm just going to move on. Okay. Okay, p-value as quick as we can. Let's say we have a hypothesis. Exercise improves sleep. And we've done it the right way because we've assigned some to exercise, some to not, and we get a p-value of 0.032. If the p-value is less than your alpha, which your alpha is typically 5%, if it's less, we call that statistically significant. So we can conclude exercise improves sleep. Now, I use the same exact example. This is something you have to study. If it's less, it's rare, it's small, and you say it is statistically significant. But let's say we did the same thing. We assigned some to exercise, some don't exercise, and our hypothesis, exercise improves sleep, but we get a p-value of 0.332. Well, that would be greater than 5%, so it's not statistically significant, and we can't conclude that the exercise improved sleep. All right, trying to jump into some of these to try to finish these up. I don't know if I'm going to make it. Number 12, which of the following is an example of random sampling? Picking out of a hat to assign those. Okay, that sounds like it, but when you pick out of a hat, you're assigning to an experiment. That's actually randomization or random assignment. That's not random sampling. Number 2, having a computer generate a list of 100 high school students. That would be random sampling because you're choosing people randomly to go survey. Okay, so right away we can get it down to, must be B. Okay, approaching any 50 students during 6th period, that's not random. When we implement our choice, that's not random assignment. No, that another bell's going to ring. I might just stop at that, but let's try to get a couple more of these done. Jose hypothesizes that a new drug he has just invented will enhance mice's memories. He feeds the drug to an experimental group and gives a control group placebo. He then times the mice as they learn to run through a maze. In order to know his hypothesis has been supported, Jose would need to use what we call inferential statistics. What does infer mean? Of course, infer means make a decision based on statistical evidence. I think I'm just going to end that there, and hopefully that was a little bit helpful.
Good morning.